Now let's look at the practice problem that has to do with figuring out how to fly to Lansing. Now you might ask the question, what does this have to do with statics and strength of material? And the real answer is, it's all about adding up vectors, and that problem is the same whether it's a navigation problem like this, or whether it's forces like we'll do in this class. The technique is exactly the same. So let's begin. Now in this problem, we have four vectors. If this is Monroe, and this is Lansing, I have three vectors, vector 1, vector 2, and vector 3. And these all add up to this vector. I know this vector, it's leg 1, it's 35 miles, and it's at a heading of 300. And I know this is 20 miles at 270. And I also know that the end result of the entire addition process is 82.5 miles at 314 degrees. Now, a couple things we want to know. When I say at 300, it means this is due north. This is the only thing different than a statics and strength of material problem, is that this angle is 300 degrees. And this angle, all the way around, is 314. And similarly, this angle is 270. So you might have to do some subtractions and additions to figure out what these angles are from the x-axis. And I've done that. But the important thing here is how to break each one up, each angle up, into its x and y components. Its horizontal and vertical components. And then we can worry about headings and that sort of thing later on. So 270 degrees is purely horizontal. 300 degrees is 30 degrees above the horizontal axis. This guy is unknown. That's what we want to find out. And 314 is 314 minus 270, so it's 44 degrees above the horizontal axis. That's not as important as breaking down the problem. So how do we do this? What's the approach? Again, first step is always break up the problem, break up each vector into its x and y components. So if I take my final result, my final destination, and I break that up into its x and y components, I end up with 59.3 miles this way and 57.3 miles that way. It's almost 45 degrees. These two should be practically the same, and they are. Okay, the other vectors that I know, 35, and again, this is at 30 degrees. So these two legs are 30.3 and 17.5. And then finally, the last leg is 270, or purely horizontal. So that's already in its x component. There's nothing else to calculate. The next thing I do is I make a table, like I always make a table. X, Y, leg 1, leg 2, leg 3, and the total. Now, this is the unknown. These other legs are the things I know. I know that the x coordinate is 59.3 and the y coordinate is 57.3. For leg 1, I know this one is 30.3 and this is 17.5. And by the way, I've got this backwards. I know leg 3. I don't know leg 2. Let's fix that. Leg 3, 20 in the x direction, 0 in the y direction. Now, this plus this plus this equals this. So 59.3 equals 30.3 plus 20 plus fx2. Easy to solve for. fx2 equals 9.0. And similarly, 57.3 equals fy2 plus 0 plus 17.5, or fy2 equals 57 minus 17.5. That's 39.8 miles. This is now leg 2. It has an x coordinate of 9.0 and a y dimension of 39.8. And I can figure out this length and this angle very easily. So leg 2 equals the square root of 9 squared plus 39.8 squared, and that equals 40.8. And theta is the inverse tangent of 39.8 over 9. And that equals 77 degrees. Now that's this angle. So if we're going to do navigation problem, this is set 270, this is 77, so my heading is 270 plus 77, or 347 degrees. Okay, I'm not too worried about the heading and that sort of thing, because that really doesn't apply, but you should be able to calculate the angle from the horizontal axis. That's what we'll always need to know. There. You now know enough to get to Lansing, and as a matter of fact, that's exactly how these problems are done. And that is all.